Hi, so this talk is on optimal deep learning for robot touch. This is joint work with between myself, Nathan Lepora, and John Lloyd at the University of Bristol and Bristol Robotics Laboratory. So what's this work about? So this work concerns this work was published in RAM, Robotics Automation Magazine paper last year and it's the special issue on deep learning and machine learning in robotics, which we're very happy to be part of. And the paper's on optimal deep learning for robot touch about training accurate pose models of 3D edges and surfaces. Now, the work is part of a larger body of work that John and I have been doing together jointly on control of touch, of tactile sensors, on basically the servo control of using tactile sensing. So we have a separate paper that has just been accepted at RAM as well on pose-based tactile servo control using deep learning. I'll discuss both of these in this talk, with obviously more of an emphasis on the paper I'm supposed to be talking about, the optimal deep learning for robot touch. So the Tactile Robotics group at Bristol Robotics Laboratory focuses on soft biomimetic optical tactile sensors, in particular the TACTIP, as it's known. So this is a 3D printed biometric tactile sensor that the skin is designed to mimic the morphology of human skin and the transduction principles of human skin. And then we've integrated this sensor into many hands and robots. This work is focusing mainly on the control, closed loop control, servo control of this tactile sensor in interaction with natural objects. And I point to a couple of reviews here, one that's just coming out and one that was published a couple of years back. Okay, so how do you control a robot using its sense of touch? So if we take inspiration from visual servo control, so standard visual servo control methods divided in, there was an important step in the 1990s of considering there to be two different types of visual servo control. One known as image-based servo control, and the other known as pose-based servo control. And that's classic work. The people who did that are now very senior figures within. So now the key point about this is the image-based control basically takes features extracted from images and does the control on those features, on the variables extracted relating to those features. And then there needs to be a transformation from, if you like, the control in image space, if you like, to the control of the robot, joints and so on, that's needed to move the robot. So that's image-based control, image-based servo control. The second type, pose-based servo control, considers instead that you extract the pose of the contact of how say that you're trying to you servo control onto an object. You want to estimate the pose of that object relative to the camera, and then control the camera in order to visually servo onto the object. So the estimation of pose is more complex from the image, but then once you've got the pose, the control of the robot is actually a lot simpler. So this work has been influenced by Chan Lee's work on the control framework for tactile servoing, where he's considering image features from a rigid planar array, and so extracting features such as center of contact and feeding that into the control loop, which could be considered as being analogous to the image-based servo control. And the approach we're considering here is to control pose more directly using the convolutional neural network to extract the pose, which applies to soft curved tactile sensors such as the TACTIP, which is more we would consider the analogy of pose-based servo control. So our contributions to use deep learning, convolutional neural networks to predict the pose of an object, address two issues that come up if you're trying to use soft tactile sensors such as the TACTIP to predict those pose, which we refer to as the shear and variance problem and the hyperparameter tuning problem. And then I'll consider some demonstrations of pose-based tactile servo control to illustrate how those methods work. Okay, so pose prediction with tactile images. The idea here is to use a PoseNet. So it's a deep neural network which takes as input the tactile image and as output the pose parameters for the object or for the feature, for the part of the object that's being contacted. So in this case, we considered two types of local object component part feature. One is servo control over a surface, predicting the pose of a surface relative to the sensor, and the other is predicting the pose of an edge relative to the sensor. For the surface, there's three pose components to be predicted: the orientation of the sensor relative to the surface, and the depth. And then for an edge, there's five pose components to be predicted. Basically, because for a straight edge, you can't get information about where you are along the edge, but you can get information about the other five components. So we used a supervised deep learning framework where we trained the network with randomly sampled poses and about 2,000 for train validation tests, with some subtleties that I'll come to in a minute. So that works very well once these subtleties are catered for. So you can see here, like this ground truth against predictions, you know, they're close to the line of equality, particularly for the surface. There's, you know, small errors about a fraction of 0.1 of millimeter and a fraction of a degree. And then for the edge, pose prediction accuracy, maybe not quite so accurate, but still good. We're talking about sub-millimeter and degree level accuracy. I should say these are the results from the original RAM paper. These results have improved with the second paper that's in publication at the moment. But basically, we used more data to train the networks. Okay, so now the problems. So the first problem is what we refer to as shear and variance issue, which is the problem is that sliding a tactile sensor over a surface deforms the tactile image, and that deformation of the tactile sensor due to the sliding, it so interferes with the information in the tactile image due to the pose of the contact. So, for example, here the columns show pairs that have similar poses, contact, and the rows show different ways of two different examples of sliding onto those poses. And you can see that actually there's more variation in the tactile images due to the sliding than there is due to the pose, in this case, due to the pose of the contact. So that makes it a challenging problem to extract that pose information from, if you like, all the other information about contact that's going on. A solution was to introduce unlabeled shear perturbations into the training data collection. So you can consider this a form of physical data augmentation, where as the labeled pose data is being collected, then unlabeled shearing perturbations are introduced into the data collection so that is represented in the training data. So here being an example of how that might be done, for example, slides before you take before you extract the data from the pose. Now, the second issue is the hyperparameter tuning issue, which is the problem. Once you do this to train your networks, then we found that the trained networks, the performance of them became highly dependent upon the hyperparameters for the neural network, things like the number of layers, number of convolutional filters, and so on. So it made it become basically almost impossible to tune manually by hand to find a good network. So we had to resort instead to using Bayesian optimization over the hyperparameters to find a good model, a good predictive model. So, and here being an example of the Bayesian optimization, and you can see the variety of losses that you get for these models while it's training using while it's optimizing the hyperparameters using Bayesian optimization. And then as I emphasized, this is because of the physical augmentation that was introduced to get around this shear issue. Okay, so then Posebased server control, I won't focus too much on this, but basically say it's analogous to a pose-based visual server control loop, but here using the tactile images to estimate the pose of the contact. That's then fed into a PID controller with a reference pose that basically determines the orientation of the sensor relative to the surface. The tricky thing is you have to be very careful about the coordinate frames and the notation and how these are handled in the code. But otherwise, it can basically be viewed as a PI controller in this case. Okay, so here's some examples. Firstly, some simple surfaces. So this is servo control on a ball. And from these tactile images here. So as you can see, it basically works, and it works very accurately, even though the sensor's sliding over the surface. A simple edge. So here's around the edge of a saddle. So again, this is working now on using the 5 pose parameters in this case to predict the state of the sensor relative to the surface, and then that being controlled with the PI loop so that it can servo around the object. More complex cases. So the tricky thing here is this was trained on a flat surface, but in this case, on a flat plastic surface. In this case, it's been given a surface with quite different frictional properties, and it's very curved. But if you like, the magic of deep learning and the robustness that's built into the network through the training allows the predictions to generalize quite well to this unfamiliar situation, to the extent that you can get this accurate pose-based server control on this complex object, particularly like, say over the nose there. Okay, and then another example of a complex object. So this is a container lid taken from the YCB object set. So here the tricky thing is, again, this doesn't really look like the edge it was trained on, which was the edge of one of the circles. So some of these edges are very rounded, look quite unlike what it was trained on, but still, nevertheless, because the network generalizes well, that accurate server control is reached. And then here's a load more examples of it working on a variety of different objects. So basically, as a method, it works robustly in a range of different 3-dimensional scenarios, which is what you want from a tactile servo controller. Okay, so to give some conclusions, so the PoseNet predicts the local pose of surfaces and edges needed to solve the shear invariance and the hyperparameter tuning problems to high accuracy, sub-millimeter, sub-degree. And then we combine that with pose-based server control to generalize, and it generalized well to a variety of objects, shapes. Future work, we've been looking at this using similar methods for object manipulation. And in particular, there's a paper just been accepted by John and myself in Transactions on Robotics on pushing objects, non-prehensile manipulation objects using this using related methods, and future work as well to look at soft objects. I'll say thank you to the lab that did the hard work, whereas I just talk about the work. And just to finish, here's it working on a soft object. So thank you for listening.